Section, Part. In the past few years, large language models have proven their ability to handle a wide array of tasks due to their strong generative capacities. To guide the output of these models, we often use a process called prompting. This method involves providing task instructions, context, or a handful of examples to condition the generation process. Despite their capabilities, smaller language models often struggle with issues like hallucination, degradation, and meandering when generating language. Various solutions, such as instruction fine-tuning and reinforcement learning, have been proposed to address these problems. However, these methods are computationally expensive and not everyone has access to the resources required to employ them. In this paper, we introduce a method that focuses more on the user's intent, as conveyed through the prompt, during the inference stage. Our primary hypothesis is that a stronger focus on the prompt during inference will lead to generated outputs that better align with the user's expectations. We also note that similar issues exist in the field of text-to-image generation. Standard methods sometimes overlook parts of the prompt conditioning, especially when dealing with unique or uncommon prompts. A technique called classifier guidance has been suggested to improve the generative quality of diffusion models by using a separate classifier to enhance desired traits in the output image. Classifier-Free Guidance, CFG, was then introduced as an improvement upon this, in which the classifier is eliminated and the generative model itself is implicitly used as a classifier. Encouraged by the effectiveness of CFG in the domain of text-to-image generation, we have adapted it for use in unimodal text generation. While diffusion models, primarily used in text-to-image models, require specific training to employ CFG, we find that CFG can be readily used in many situations for text generation. In this paper, we show how CFG can enhance a broad spectrum of prompting techniques such as zero-shot prompting, chain-of-thought prompting, long-form generative prompting, and complex chatbot-style prompting. Here are our key contributions. 1. We've developed a framework that applies CFG to language modeling, showing notable enhancements across a variety of standard benchmarks. These benchmarks encompass several different prompting techniques including basic prompting, chain-of-thought prompting, long text prompting, and chatbot-style prompting. Most notably, we achieve state-of-the-art results on the Lambda benchmark with our Llama 7B model, surpassing the Palm 540B model. 2. We demonstrate that for the same computational cost, one can train a model that is half the size, yet yields similar performance on the aforementioned benchmarks. 3. We show that by using a negative prompt, we can have finer control over the characteristics highlighted by CFG. Through a blind human evaluation, we demonstrate a 75% preference for our GPT-4 model using CFG over standard sampling. 4. We provide qualitative and quantitative interpretations of the impact of CFG on text generation. Qualitatively, we illustrate how CFG increases the weight of words more related to the prompt. Quantitatively, we show that CFG reduces the entropy in the sampling distribution, implying a more predictable and focused output. Our visualizations underscore how effective prompt engineering can leverage the use of CFG in text generation. Section Summary. In this paper, we propose a methodology that focuses more on the user's prompt during inference time to improve the generation of language models. Inspired by the success of Classifier-Free Guidance, CFG, in text-to-image generation, we adapt CFG to unimodal text generation and demonstrate its effectiveness in improving various prompting approaches. Our framework using CFG achieves state-of-the-art performance on different benchmarks, allows for training smaller models with similar performance, and provides more control over the generated output. Section 2 Methodology. We are focusing on the methodology of using autoregressive language models in the generation of relevant continuations for given text sequences. We take a sequence of words, or tokens, and then the model samples each subsequent token based on the probability distribution of these tokens. Some or all of the first few tokens are treated as a prompt, providing task-specific information or instructions on how the task should be solved. However, in reality, these prompts are different, both syntactically and semantically, from the rest of the text. The standard generation techniques employed by large language models do not differentiate between these prompts and subsequent generations. This could lead to generated continuations that deviate from the initial prompt over time. Inspired by successful results from diffusion models, we're proposing a solution to this problem by integrating classifier-free guidance into the decoding process of autoregressive language models. In the realm of text-to-image models, we aim to condition the generation on a given label or text description during inference. These generative models typically create data from an abstract representation, like the latent vectors in GANs or the intermediate sampling steps in diffusion models, which is then decoded into an actual sample. The process of control generally entails guiding or adding constraints to this abstract representation. In classifier guidance, we introduce an auxiliary classifier that guides the sampling process to increase the likelihood of a given label for generation. This results in samples from a new distribution, which reweights the density according to the classifier's likelihood. The strength of this reweighting is controlled by a factor denoted by gamma. If gamma equals 0, it results in an unconditional generation, while gamma equal to 1 results in a conditional generation. When gamma is greater than 1, it overemphasizes the conditioning, which has been observed to enhance inception scores, albeit at the cost of diversity. Now, the concept of classifier-free guidance comes into play. Using Bayes' rule, we realize that we can do away with the need for an external classifier. By training the same model to support both conditional and unconditional generation with conditional dropout, we can rewrite our formula accordingly. Then, the sampling is performed according to a modified probability formula. With this, we model the diffusion process, which involves predicting the probability distribution function, PDF, of the sample noise. This process is significantly important when working with diffusion models. Moreover, we introduce the concept of negative prompting, which is essentially a vector arithmetic operation in latent space. It involves moving a step of size gamma away from the unconditional vector in the direction of the conditioning. This kind of semantic vector linear arithmetic has been effective in many situations in vision, especially in GANs or diffusion models. We also introduce the idea of negative conditioning, or negative prompt, which is a generalized equation that arises when the negative prompt equals an empty set. This equation again represents a step in vector arithmetic in latent space. Section summary. In this section, the authors discuss the problem of generating text continuations that lose adherence to the initial prompt in autoregressive language models. They propose applying classifier-free guidance to address this issue by reweighting the density according to the classifier likelihood. They also introduce the concept of negative prompting, which involves taking a step away from the unconditional vector in the direction of the conditioning, allowing for more control over the generation process. Section 2.2 Classifier-Free Guidance of Language Models. We'll be discussing how to use classifier-free guidance, CFG, with language models. The first step is to determine the semantic space we'll work in. Prior research has shown that word and sentence embeddings carry a lot of semantic information. Consequently, we use token prediction logits as our latent space, due to their linear relation with the final hidden layer. Utilizing these logits allows us to avoid network modification and is compatible with various architectures. Next, we must specify what we regard as conditioning, denoted as C, in our language models that use only a decoder. Typically, a user provides a prompt, C, which might be context, a command, or the start of some text. The user then uses the language model to generate a sequence of continuation tokens corresponding to the prompt. Because a good continuation should closely correlate with the prompt, we identify the prompt as our conditioning. Following the steps of classifier guidance, our goal is to create text that is likely to start with C. We define a reweighted distribution based on two probabilities: the probability of text W, given C, and the probability of C, given W, which we adjust with a factor, gamma. We approximate this distribution using CFG. The distribution is also redefined in terms of the probability of W, given C, raised to the power of gamma, and divided by the probability of W, raised to the power of gamma, minus 1. In autoregressive language models where the probability of a word sequence, W, is the product of the probabilities of each word, W_I, given all the words that come before it, we can simplify this distribution. The final expression for this model has the form of the probability of W, given C, to the power of gamma, divided by the probability of W, to the power of gamma, minus 1. It's important to note that while diffusion models conditioned on some input can't predict distributions without further training, language models can handle both the probability of W, given C, and the probability of W, naturally. This is because they are trained on finite context windows, which means dropping the prefix C is naturally feasible. Therefore, we can calculate the log probability of the next token, W_I, using the formula that combines the log probabilities of W_I, given previous words, with and without conditioning on C, and the difference between these log probabilities is scaled by gamma. Furthermore, this formulation can be expanded to include negative prompting, a topic we'll explore in more detail in a future section. Now, we'll move on to the experimental section where we'll investigate how CFG affects different forms of prompting. Section summary. Classifier-free guidance, CFG, can be applied to language models by using the logits of token predictions as the latent space, which has a linear relationship with the last hidden layer. In decoder-only language models, the prompt provided by the user is considered as the conditioning, and the goal is to generate text that starts with the prompt. The CFG formulation approximates the distribution of the generated text using a gamma-reweighted distribution, allowing for sampling of the next token in the logit space. Section 3 Experiments. In this part of our study, we demonstrate how the Classifier-Free Guidance (CFG) method notably enhances results across multiple common prompt-based techniques. To begin with, we have discovered that CFG remarkably enhances performance in scenarios that don't require prior learning or training, known as zero-shot performances, on a range of typical natural language processing (NLP) benchmarks. Among the successes was achieving a record-breaking performance on Lambda, using Llama 7B. We have also applied CFG to the chain of thought prompts, which first enable the model to reason before responding to a question. In addition, we assessed the efficacy of CFG on prompts for text-to-text generation. Finally, we established that CFG could be employed for assistant prompts, which are prompts that contain system instructions. To explore the efficacy of basic, zero-shot prompting, we implemented various zero-shot benchmarks using the language model evaluation harness. These benchmarks include tasks like closed-book question answering, common-sense reasoning, and sentence completion. Generally, the desired completions for these tasks are brief, typically 1 to 2 tokens, reducing the risk of straying off topic or output degradation. We theorized that the main influence of CFG in these contexts would be to decrease output variation, which we delve into more later. We conducted our evaluations using the GPT-2, Pythia, and Llama model families with various strengths across a range of standard NLP benchmarks. We integrated CFG by initiating the unconditional prompt at the last token of the original prompt. We have visualized our results in charts and a table. The graphs display the performances of the GPT-2, Pythia, and Llama models across the standard benchmarks. In all cases except ARC, Challenge, and Winagrande, the enhancement in performance using CFG was substantial and consistent. The reasons for the disparities in these two cases remain unclear. Intriguingly, we found that even the smallest Llama 7B model, with gamma set to 1.5, reached an 81% accuracy level in the Lambda, OpenAI, zero-shot benchmark. This performance surpassed the existing top score of PaLM 540B, which had achieved a 77.9% accuracy level. Even though the use of CFG roughly doubles the computation during inference, the comparison is still remarkable. This is because other models that have similar performances on Lambda, OpenAI, come with a larger number of parameters, which would require even more computational resources than the Llama 7B model when used in conjunction with CFG. In conclusion, our experiments provide robust evidence that CFG considerably enhances performance in basic prompting scenarios. Section Summary. In this section, the authors demonstrate that Classifier-Free Guidance, CFG, improves performance across various prompting approaches. They apply CFG to zero-shot prompts, chain-of-thought prompts, text-to-text generation prompts, and assistant prompts. The results show that CFG consistently enhances performance, achieving state-of-the-art results on benchmarks such as Lambda. Despite the increased computation during inference, CFG proves to be a valuable technique for improving performance in basic prompting settings. Section 3.2 Deliberative Prompting, Chain of Thought. We've been exploring a variation on the usual prompting approach, which we call the chain of thought (COT) method. In this method, we ask the AI model to go through a series of reasoning steps before coming up with an answer to the task at hand. The goal here is to mimic how humans reason or deliberate. Think of the process as a sequence of words where the chain of thought, notated as W_COT, includes all the words from just after the prompt, W_P+1, to the word before the final answer, W_C1. The final answer is represented by W_A. Interestingly, this chain of thought prompting method has been effective in dealing with complex reasoning tasks that cannot be fully addressed by just scaling the model or the data. However, we have observed that if the reasoning chain is too long, it can go off course, leading to incorrect answers, or not aligning with the expected result structure given by the prompt. Now, compared to the previous basic case, the continuation of words, notated as W_C, and including the chain of thought and the final answer, is expected to be more than just 1 to 2 tokens. We believe that, just like with basic zero-shot prompting explored earlier, our method, Control Flow Graph, CFG, will help enforce better reasoning chains with less drift. We've tested the effectiveness of our CFG method with respect to chain of thought prompting on two arithmetic reasoning tasks, namely GSM-8K and Aqua. Our experiments were done using two open-source language learning models, LLMs, WIZARDLM30B and Guanaco65B. What we found was that using CFG increased the percentage of chain of thought prompting that resulted in a valid and parse-able answer. When the strength of the CFG was low, it helped boost the performance of the model. But when the CFG strength was high, even though the model returned more valid results, the quality of the reasoning chains was affected, leading to overall poorer performance. To make it clearer, we've provided a side-by-side comparison in table. We are still in the early stages of understanding how CFG interacts with chain of thought prompting. For example, we might try to increase the weight not just of the prompt, W_P, but also of the chain of thought, W_COT, among other variations. In future, we hope to investigate more variations of CFG weighting on different parts of the COT process. Section Summary. Chain of thought, COT, prompting is a variation of basic prompting where the model is asked to generate a series of reasoning steps before providing an answer. This approach has shown promise in complex reasoning tasks, but long reasoning chains can lead to incorrect answers or deviations from the expected structure. The authors propose a method called CFG to improve the reasoning chains in COT, and their evaluation shows that CFG can enhance model performance by increasing the percentage of valid answers, although excessively high CFG values can degrade overall performance. Further exploration of CFG's interactions with COT is suggested for future work. Section 3.3 Text-to-Text Prompts, Generation. In this segment, we shift our focus to instances where generating extended responses, rather than just short answers, is vital. Such circumstances often arise in tasks such as coding, where an initial prompt necessitates a more extensive, focused follow-up to be effective. This puts a spotlight on our model's ability to maintain consistent thematic focus over an extended sequence of text. We'll first examine this phenomenon in the context of code generation and then, for a more in-depth analysis, delve into machine translation. You'll find those results in the appendix. 3.3.1 Evaluating program synthesis coding represents a fascinating case for language modeling because, unlike natural languages, formal coding languages rely heavily on well-structured syntax. We subjected our model, Classifier-Free Guidance, to a variety of coding tasks, and found that it performed well, thus strengthening our original hypothesis across different data distributions. We began with some preliminary experiments, prompting models GPT-J and CodeGen 350M Mono to generate small-scale code snippets. The results were encouraging. Check out the appendix for more. We then followed up with a comprehensive evaluation using the Human Eval benchmark. 3.3.2 Using the Human Eval benchmark, we wanted to systematically explore how well classifier-free guidance fares in code completion tasks. The Human Eval benchmark gave us an ideal testing ground. It consists of 164 coding tasks in Python, each given a function signature and a docstring as prompts. The task for our model was to provide the remaining code. We then tested the generated code against a set of unit tests designed for each task, judging the correctness of the Python programs. We tested this on three models, CodeGen 350M Mono, CodeGen-2B Mono, and CodeGen 6B Mono, all of which are specially designed for Python program synthesis. We omitted CodeGen-16B Mono due to computational limitations. We tested the models with various strengths of classifier-free guidance at different levels, from 1.0 to 2.0. We also examined performance at three temperature settings, 0.2, 0.6, 0.8, using a metric called pass at K, where K could be 1, 10, or 100. In the context of this experiment, pass at K means that if we generate K code samples per problem, a problem is deemed solved if any of these samples pass the unit tests. We report the overall percentage of problems solved. We noticed a trend that lower classifier-free guidance strengths, below or equal to 1.5, consistently increase the pass at 1 rate. However, when the strength increases beyond 1.5, performance deteriorates. Interestingly, this improvement seems to become less significant or even detrimental as the value of K increases. To probe deeper into the effects of classifier-free guidance, we performed a detailed analysis of pass at 1 rates for the CodeGen 350M Mono model with strengths of 1 and 1.25, on a task-by-task basis. We found that for all tested temperatures, 0.2, 0.6, 0.8, classifier-free guidance outperformed in more tasks than it underperformed. In fact, several tasks had small yet non-zero passing rates without classifier-free guidance, which dropped to 0 when it was introduced. This might explain why the improvement from classifier-free guidance seems to diminish for larger K values, as it could increase the passing rate for more difficult tasks that previously had low but non-zero passing rates. In conclusion, while we've observed that classifier-free guidance consistently improves pass at 1 rates, this advantage seems to reduce at higher K values. We hypothesize that while classifier-free guidance bolsters adherence to the prompt, it may do so at the cost of reducing variability and creativity. Section Summary. In this section, the authors explore the use of classifier-free guidance, CFG, in a prompt setting where longer answers are required. They focus on code generation tasks and evaluate the effectiveness of CFG on a human eval benchmark, which consists of 164 coding tasks in Python. The results show that low CFG values, gamma is less than or equal to 1.5, improve the pass rate at the first attempt, while high CFG values, gamma is greater than or equal to 1.5, lead to a decrease in performance. Additionally, the authors find that CFG strengthens adherence to the prompt but reduces variability and creativity. Section 3.4 Negative Prompting, Improving Assistance. Finally, we investigate an enhancement to our classifier-free guidance, which we refer to as negative prompting. Negative prompting involves instructing the AI about what to avoid in its output. This might be particular phrases or undesirable traits like low resolution or bad anatomy in a text-to-image context. The goal is to utilize this strategy to enhance the quality of the generated output, with our main focus being chatbots. Chatbots are an ideal testbed because they allow us to extend the initial prompt into a multi-stage prompt. This mirrors the way COT prompting evolves the continuation into a multi-stage completion. In this chatbot setting, the AI receives a two-part prompt. The first is a system prompt that may offer context such as the current date, or guidelines on behavior, persona, style, and so on. The second part is the user prompt, essentially the query from the user. Yet, adhering to these prompts can be quite challenging. We noticed that systems like Alpaca often disregard alterations to their standard system prompt, potentially making them vulnerable to prompt injection attacks. To tackle this, we're exploring the combination of classifier-free guidance and negative prompting to improve adherence to different system prompts. We designate the default system prompt used by the models as the negative prompt. The edited prompt is then used as the positive prompt. For example, the default might be, the prompt below is a question to answer, a task to complete, or a conversation to respond to. Decide which and write an appropriate response. This could be edited to, decide which and write a sad response. This technique not only enhances the model's awareness of the prompt but also highlights the distinction between our system prompt and the model's default system prompt. To test this approach, we create a number of system and user prompts, and randomly combine them, generating 1740 combinations in total. We then use the GPT-4 All-J version 1.3 Jazzy model to generate 2 responses for each combination, one without classifier-free guidance, and one with it, the strength of which is randomly chosen from the range 1 to 6. Our theory is that classifier-free guidance increases adherence to the system prompt, without reducing the relevance of the user input. To validate this theory, we conduct a study where participants compare the generated responses. They evaluate which response better follows the system prompt and which one better follows the user prompt. Our findings, depicted in figure, provide strong evidence that classifier-free guidance significantly amplifies the contrast between the system prompt and the default system prompt more than when using the system prompt alone. We noticed a noticeable preference peak for system prompt following when the strength of classifier-free guidance was set to 3, with 75% preference over a setting of 1, while user prompt relevance remained largely unaffected, 52%. Section Summary. The paper introduces a technique called negative prompting, which allows users to specify what they do not want in the output of AI assistants. This approach is explored in the context of chatbots, where the prompt is expanded into a multi-stage instruction. By using negative prompting, the success rate of different system prompts is increased, as shown in a human preference study. Section 4 Computational Cost Analysis. In our previous discussion, we demonstrated how our new, classifier-free approach has brought improvements to various benchmarks and contexts. Now, you may be wondering, if this approach requires 2 passes through the neural network, isn't it computationally expensive? Maybe I should just stick to running a larger model? To address this, we carried out an analysis of computational cost, measured in floating point operations, flops, for each benchmark experiment we ran. We compared the computational cost of different model sizes, with and without our classifier-free approach. Our results were surprising. For 5 out of the 9 tasks, There was no significant difference in computational cost between using our approach and running a model that's twice the size, at a significance level of 0.01, according to ANCOVA regression analysis. Among the tasks that showed significant differences, 2 of them favored our approach, and 2 of them favored the traditional, vanilla, method. You can find a more detailed breakdown of our results in the appendix, particularly Figure X. The big takeaway here is that, in general, a model using our approach can perform just as well as a model that's twice as big. This has significant implications for training budgets and processing speed, especially when working with limited VRAM. We're keen to delve deeper into these aspects in our future research. Moving forward, we'll try to understand why our classifier-free approach has been successful. We'll analyze its effects on generation from both a quantitative and qualitative standpoint. To do this, we sampled a dataset of 32,902 data points from the P3 dataset and used the Falcon 7B base model family for exploratory purposes. We're mainly interested in analyzing the distributions of logits, logarithmic odds. We'll explain how in the upcoming sections. Much of our analysis will reference an instruction-tuned model, for which we'll use the Falcon 7B instruct version. We have also replicated our findings on other models and datasets, including the Open Assistant dataset and the REDPAJAMA3B model family. One of the effects we've noticed from our approach is its impact on sampling entropy. We hypothesized that our approach, by concentrating the probability distribution of the next output, text P, Y, X, on the prompt, would decrease the entropy of the logit distribution. And indeed, the entropy of the logit distribution under our approach was significantly lower compared to vanilla prompting, with averages of 4.7 versus 5.4. This effectively limits the number of tokens in the top 90% of the vocabulary distribution. Although the top tokens didn't change much, they did rearrange a bit. This indicates that our approach isn't merely duplicating the effect of a temperature parameter. Section summary. The computational cost analysis revealed that, despite requiring 2 passes through the network, using classifier-free guidance, CFG, can yield similar performance to using a model twice as large. In terms of flop, this finding has significant implications for training budgets and inference latency due to limited VRAM usage. Additionally, the analysis of CFG's impact on sampling entropy showed that it reduces the entropy of the logit distribution, resulting in a more focused distribution of tokens in the vocabulary. Section 5.2 CFG's relation to instruction tuning. In the next part of our study, we delve into how classifier-free guidance, CFG, interacts with vocabulary distribution. We were curious whether CFG has the same effects as instruction tuning, a process believed to train the model to concentrate on the prompt. When we compared the CFG and instruction-tuned models, we found that both had similar entropy levels across generated samples. But when we examined vocabulary distributions, there wasn't much overlap. This refuted our initial assumption: CFG doesn't affect vocabulary logits in the same way instruction tuning does. We were determined to dig deeper and aim to learn from instances where CFG does mimic instruction tuning. We sought out characteristics that could explain when these similarities arise, particularly in relation to the level of overlap between the top P, most probable, results. We found an interesting trend. When the prompts were longer, CFG showed more agreement with instruction tuning. Specifically, we noticed a notable Spearman correlation of 0.05 between prompt length and the degree of agreement between the instruction and CFG models. Furthermore, we observed a slight yet significant correlation between the complexity of the model, expressed as perplexity, and the level of agreement. We noticed that phrases which the instruction-tuned models found more challenging often aligned with the CFG models. Therefore, we deduced that CFG modifies the model in ways that could potentially complement instruction tuning. This observation has paved the way for further investigations. Finally, to provide more insight, we qualitatively analyzed the reordering of vocabulary that occurs after applying CFG. The underlying equation can be verbally expressed as the log probability of a word at a given time, t, given the previous words in a certain context, c, can be rewritten as the sum of the log probability of the word given the previous words and the absence of a specific context, plus a factor, gamma, multiplied by the difference between the log probability of the word given the previous words and the context, and the log probability of the same word given the previous words and the absence of the context. This is our proposed method for visualizing the impact of CFG at each time step. We rank the vocabulary by the difference between the log probabilities of the word given the previous words, and the word given the previous words and the predicted next word. This approach reveals the tokens that the CFG method encourages or discourages the most. For example, when we prompted a model with "the dragon flew over Paris, France," and no specific context, we found that the tokens related to dragons and Paris were given more weight. On the other hand, tokens related to other locations, Queensland, dates, 1913 inches, or other topics, hostages, voyages, were given less weight. These observations corroborated our initial assumptions. CFG encourages tokens related to the prompt and discourages unrelated tokens. We discovered that this visualization method is a valuable tool for prompt engineering. By setting the new prompt under testing as the context and using the current baseline prompt as the absence of a specific context, the visualization reveals the effect of the change on the entire vocabulary for the next token prediction in a way that can be easily interpreted. Section Summary. The study investigates the impact of Classifier-Free Guidance, CFG, on the vocabulary distribution and compares it to instruction tuning. The results show that while CFG and instruction-tuned models have similar entropies, their vocabulary distributions are largely non-overlapping. However, when the prompt is longer, CFG aligns more with instruction tuning. Additionally, qualitative analysis reveals that CFG encourages tokens related to the prompt and discourages unrelated tokens, making it a useful prompt engineering tool.